Let us say we are understanding what happens to an object when it is projected from a height on the Earth's surface. So we devise a thought experiment, also called as Gedanken in German. So let us say we move to a certain height h above the surface of the Earth. That height h is not very huge. It's a small height above the surface of the Earth. And if we fire a cannonball, let us say, now that cannonball, if it is fired with orbital velocity, then we have seen that it will follow a circular trajectory. So this circle it will follow if it is fired with orbital velocity, and then it will revolve around the Earth with orbital velocity. So what do I mean by orbital velocity? If it is fired for this particular trajectory to be a circle, it has to be fired with orbital velocity, which we have just seen to be under root of gm upon r plus h. So if it is fired with this particular velocity, it will keep moving in a circle. So if it is fired with lesser velocity, then it will tend to move in an ellipse. So this is the ellipse that it will tend to move in. Let us say it is fired with even lesser velocity. In such a case, then it will fall directly to the earth. So this is also an ellipse. This trajectory is also an ellipse. However, the earth got in the way basically, and hence it cannot complete the ellipse basically. However, if you analyze around the center of the earth, so let's say this is the center of the earth, if you could analyze, or if this trajectory were to proceed, then it would have been an ellipse like so. Alright, so if we fire with slightly more than the velocity of the orbit, which is Vo is equal to under root gm upon r plus h, but less than something called as the escape velocity. The escape velocity from the surface of the earth, Ve, happens to be equal to under root 2 gm upon r. This expression will soon derive. In this expression, it is assumed that h is approximately 0. So we are firing from the surface of the earth. This is what is assumed in this particular expression. So if we do fire with Ve, then this particular cannon is going to go along this parabolic trajectory, and it will escape to infinity. It will escape Earth's gravitational pull and it will move to infinity. So if we fire with greater than Vo but less than Ve, then it will follow an ellipse that is larger than the orbital circle. So this is the orbital circle with which along which it will move if the cannon is fired at Vo velocity. If it is fired at more than Vo velocity but less than equal to Ve velocity, then it will go, rather to be exact, less than Ve velocity, then it will go along an ellipse. If it is fired with Ve velocity, then it will go along a parabola to infinity. It will escape to infinity. And this hyperbola that we see over here, that is for velocity of projection to be greater than Ve. So if it is fired with greater than V velocity, then it will go away to infinity in a hyperbolic trajectory. So these are the conic sections that Kepler found are the trajectories of an object that is fired from the Earth's surface with certain appropriate velocities. So let us find out the expression for Ve, which we promised that we'll derive. So let us say this is a rocket. We are wanting to launch a rocket in space, let us say. So this particular rocket should be launched and it should move to infinity. Let us say we want the rocket to escape the gravitational pull of the earth. Now in order for this rocket to escape the gravitational pull of the earth and move away to infinity, the important point to be realized is the angle at which the rocket is fired does not matter. So it could be fired at any angle. So let us say the rocket is fired at this particular angle, then it will move like so to infinity. So the angle at which this rocket is fired is not going to actually matter. The only thing that matters is the velocity with which it is going to be fired. Why? Because For understanding how it reaches infinity, we are going to use the energy conservation equation. So the initial energy of the rocket, let's understand what's the initial energy. So this happens to be the center of the earth, and this is the line joining the center of the earth to the rocket. So basically the rocket is at a distance r, which is the radius of the earth, which happens to be approximately 6400 kilometers. So r is the radius of the earth, and the rocket has the initial potential energy that can be written as g into mass of the earth into mass of the rocket divided by r. This is the initial potential energy of the rocket. So minus g mm upon r, and we are giving it a velocity v. So the initial velocity of the rocket is going to be half m v square. With this velocity it will escape to infinity. What is the meaning when we say that it will escape to infinity? What does it mean? Basically it will reach infinity with almost zero velocity. That is what it means when we say it will just escape to infinity. So when it reaches infinity, so this is the potential energy while on the surface of the earth, and this is the kinetic energy on the surface of the earth. So when this rocket, so this is the initial position of the rocket. So when this rocket escapes and this rocket reaches infinity, let us say infinity is over here. As of now we are assuming that this is where infinity is. Actually infinity is at infinite distance, but right now I cannot show infinite distance, so I am assuming that this is infinity. So as it has reached infinity, its kinetic energy is going to be 0. So kinetic energy will be 0 and energy will be conserved. So kinetic energy will be 0, and potential energy, because potential energy is given as minus gmm upon small r, so potential energy is also going to be 0 at infinity essentially. So potential energy is 0, so you can say potential energy is 0 because potential energy is given as minus g mm upon r. So this tends to 0 as r tends to infinity. Kinetic energy is 0 because it just reaches infinity. So this is kinetic energy. So these two values are at infinity, and these two values are at the surface of the earth. So it just reaches infinity, so kinetic energy happens to be 0. So because of this particular expression, we can say that if we cancel out the mass m, then we can say ve square is equal to 2g capital M upon r. Therefore ve is going to be equal to under root of 2gm upon r. So this is the expression for the escape velocity. Alright.